Good morning, everybody. I want to take you away from the dark side of the universe back to the dark side of double beta decay. And people who know me in the past, I have been doing nuclear matrix element mostly for charge exchange reactions. These are related to 2-neutrino double beta decay. And over the time, we've taken up the challenge to look into the neutrinoless double beta decay matrix element. This is where some novel approaches come from. And let me just see if I get this correct here. Okay, so we've been talking about charge exchange and also on masses. What do masses have to, mass measurements have to do with neutrinoless double beta decay? I will explain that to you. And in the end, I will talk about muon capture. So this is my agenda. So the first 2 points I will flash over very quickly because it's already been said many times, and people who know me that they see that some of these the data, they reappear every time in the same way. So some general features. Then I talk about charge exchange reactions, helium-3T and dihelium-2. These are for 2-neutrino double beta decay. So this is not the particularly the most interesting cases, but I will tell you that there are some things that are quite interesting, and some of the surprises came out there. Then I will turn into charge exchange reactions looking for other multipoles, the 2 minus states in particular. And there we've seen a lot of surprises. And I've worked with Yoni. Is he not around? He just left. And even Yoni was quite surprised about the outcome of that. Then we talk about 2 totally different aspects, mass measurements and muon capture. So over the week, we have heard a lot of the quenching of the gamma of Taylor of the axial-vector coupling constant. Okay? I always state that the quenching of the coupling constant is a theoretical issue. And experimentalists have nothing to do with it. So experiment theorists have invented the quenching, and they should fix it. That was my position, but over the time you get a little more mellow, and then you say, yeah, I can help you in fixing it. And I will show you how to do this with this part here. And the zirconium-96 is a golden case for doing this. And the next one is the muon capture. It gives you a direct access to the GA quenching. Okay, so I flash over the first 2 things very quickly. Some general features about these decays. We heard that several times. The thing that I want to stress here is, again, if you have 2-neutrino double beta decay, this is a low momentum transfer phenomenon. That means it is related to the ordinary beta decay, and it's the sequence of 2 beta decays. And because of that, it is accessible through charge exchange reactions. You go through this branch, and you have to do the charge exchange reaction on the other one, and then combine these 2 things. Okay, so this is the formula for doing this, to remind you. Okay? So it's a beta decay into an excited state, and from the excited state, it's a beta decay to the ground state divided by some denominator. So it's 2 sequential allowed beta decays. Forbidden decays are not there, okay? Fermi transitions do not contribute because they're different isospins. And these can be determined, these matrix elements can then be determined by charge exchange reactions in the PN, or helium-3T, and the NP direction. So by looking at the same levels, putting them together, and then you have the matrix element. The 0-neutrino double beta decay is a completely different story. It's a high momentum transfer phenomenon, so that means that the matrix elements are completely different, so you cannot compare these 2 things. And that means these are not readily accessible, the matrix elements are not readily accessible to charge exchange reactions because you suddenly have higher order components in there. The situation is not very good for this because you essentially you have to rely on theory. And this is what the theory says. Theory has a lot of entropy in there. So So if you look at this, this is the matrix element and the half-life scales with the square of it. On top of that, you have another factor of 4 unknown because you don't know what the quenching of the axial-vector coupling constant is. So this is not a very fortuitous situation, and that has to be solved, by no means. Okay, let's go to the next one. So have a look at the Gamow-Teller 2 neutrino double beta decay part. Experiments, I just want to mention that, have all been done at RCMP. And the thing that I really want to stress is at RCMP you have a resolution of 5 times 10 to the minus 25, 5 times 10 to the minus 5, 25 keV at 420 MeV, which is an order of magnitude better than a germanium counter. One has to realize that. So germanium-76 is one pathological case. And I picked this up on purpose because you see the Gamow-Teller transitions in the low energy region. There are lots and lots and lots of Gamow-Teller transitions. So a lot of entropy here. So all these things that have a red hat, that's all Gamow-Teller. And we can resolve about 70 states in the low energy regime. See, these are identified as Gamow-Teller transitions. Now, in order to get the matrix element, you have to go to the second leg. And the second leg is d-helium-2. And the d-helium-2 shows nothing spectacular, a couple of states. And now the task is to combine these two things. And it doesn't work. So these things are almost anticorrelated. So this is the d-helium-2 part, this is the helium-3T part. So nature even manages to get these things sort of just in between, just not to correlate these things. And most of the correlation comes here from the grass here, which is which you can hardly see in there. Why is that? The reason is deformation. You can easily figure out that deformation causes a spreading of the Gamow-Teller resonance. However, what is the problem here that it is so anticorrelated? The reason is deformation of mother and daughter are different. So, and the Gamow-Teller operator does not change the radial part. So you have to combine this with that, and that's typically very difficult. Okay, that was the first surprise. The second surprise was that there is no need in the matrix element for the Gamow-Teller resonance. So the Gamow-Teller just simply is not there, okay? Does not contribute at all. Going to the other extreme, the molybdenum 100. This is the spectrum of molybdenum 100. No entropy at all, okay? Everything nicely put together into the ground state. 88% of the matrix element resides in the ground state. We have heard during the week about the NME experiment. They have seen the single state dominance in their spectrum. This is nicely confirmed here because 88% of the 2 neutrino double beta decay really goes through one state only. Xenon is my last one here, then I switch to the other things. Why is xenon so stable? Oh, I should maybe, I forgot to say something. Because of that here, the matrix element for molybdenum 100 is the largest so far been measured. Whereas the matrix element for the xenon 136 is the smallest. They differ by a factor of 10 or 20 or something like that. So the question is, why is that so stable? And here we have the charge exchange reaction of xenon, and nothing spectacular. You zoom in, nothing spectacular, a number of Gamow-Teller states here and there, so there's nothing spectacular about this. Except one thing. This is, the spectrum is dominated by a 2- state. That puzzled us from the very beginning, and I will come back to that particular thing in just a moment. So in terms of the Gamow-Teller transition, nothing spectacular. So why is it so stable? If you sum up the Gamow-Teller strength function, you get something that looks like this. So because you know the half-life the gamma of Taylor matrix element, you can deduce that. It's 0.02. So I said it's the smallest one. So in terms of the other leg, the d helium-2, in order to get there at 0.02, the other leg has to be extremely small. Extremely small, so small that you cannot easily measure it. Okay? And in fact, we didn't measure it. Unfortunately, we were cut down on this, the facility closed. But there's a calculation. And in fact, the calculation says that the gamma of Taylor transition strength in the other direction is in fact very small, 3 times 10 to the minus 3. And this is what we actually calculated out of our experiment. So, and then later on came the experiment, the theory, and in fact it was confirmed this way. Okay, so I already alluded to you this funny thing about the 2 minus states. So, and the next thing was we collected all the 2 minus states. You know, the 2 minus states are very easy to identify by their angular distributions. So a typical angular distribution, they have a maximum and a finite momentum transfer, typically at between 2 and 3 degrees. So this is germanium all the way up to xenon. Okay? And you take the maximum of this cross-section and plot this as a function of A, and this is what you get out. So this is the integrated strength over the Fermi surface, where the Fermi surface is sort of defined between 0 and 5 MeV. That's sort of a little bit arbitrary. So, but most of the strength is between 0 and 2 MeV. So you see a difference between zirconium here on one side and the xenon on the other side of a factor of 35. So where does that come from? So I asked Alfredo Poves to do a calculation for me, and he did the calculation for me, and I put together the vacancy numbers times the occupation numbers in the shell model calculation. And this is what comes out, a perfect agreement. But hold your horses. This is vacancy number times occupation number. It's not yet the BM2, okay? So do I have a bit more time? Yes, I do. So then I go through, why is that? Why do we have such a strong dependence here? And the reason for that is simple shell model. Look at this thing. Look at germanium, xenon. To make a 2 minus state is very easy. You take it from the H11 half and put it into the open G7 half. You have to cross a shell, okay, and then you get this. And you have many, many nucleons here in the H11 half, so it shoots up there. The same situation is true for tellurium. The H11 half, it goes there, the G7 half, the same thing here. And what I really find amazing, that the tellurium has, if you look at the extreme, or if you weaken a little bit the shell model, because there's 2 more particles in the D3 half, the occupation here is higher than there, because some of these nucleons can go up there. So the tellurium 130 should be slightly stronger than the tellurium 128, which it is. You know, here. I should mention everything is normalized at this stage to tellurium 128 because we don't have an absolute value. So now you go to molybdenum and zirconium and you realize that is completely forbidden in the shell model because you have D5 half, G7 half, or D5 half. Now you have to place them in the 2p1f shell, and that is completely full. So in the extreme shell model, it's completely forbidden. So that is why that is so small. So, and the selenium germanium case, the p shell opens up again, and you get some strength. Now, we wanted to compare this with calculations that are being done for zero neutrino double beta decay. So you see the same spectrum here again. The yellow one is the experiment. You see that here, okay? The gray one is the QRPA that Joni Suhonen did for me, and there was some surprise, okay? The shell effects seem to have washed out completely. And if you go to a no-core QRPA, which is supposedly even better than the QRPA, the no-core QRPA calculation completely ignores the shell, the underlying shell. It's constant. Oh, sorry. Okay. It's constant. It's called constant. So no-core is the white one here. is essentially constant, and is also essentially constant here. So I find this very remarkable. If it has an effect on the matrix elements, I don't know. But it certainly tells us that there is the ground state wave function. Well, the ground state, this BM2s reflect, because they are at the family surface, they mirror the ground state wave function. So apparently there is some problems with the ground state wave function in these calculations. Okay, I still have some time, and I switch to a mass measurement. High precision mass measurement, and we do this on zirconium-96. The technique for this was already alluded to by Klaus Blaum earlier this week, so I don't have to talk about this. I simply show you the results, what came out. So zirconium-96 is special because zirconium-96 together with calcium-48 can also undergo single beta decay, okay? So you have a possibility of single beta decay, from a single beta decay into the intermediate nucleus, which is usually highly forbidden, and then it decays there. So what is the idea behind this? So we want to measure first the Q value of this transition, okay, from here to there. And at the second stage, we want to measure the single beta decay. And then you get the FT value. With the FT value, you get the matrix element for single beta decay. It just so happens that the single beta decay, the only single beta decay that is possible is the one from 0 plus to the 5 plus, and that's a unique single beta decay. So you have only one matrix element, okay? So theories cannot have an excuse. So then you confront this with theory, the theory that is aimed at describing the neutrinoless double beta decay with the same theory and in the same nucleus. That's the idea. Okay, so here again, you know, there was some what is known in the past that there is a competition between single beta decay and double beta decay. NEMO 3 has calculated or has measured this double beta decay to neutrino 1. There is a geochemical measurement which measures the total decay rate. And out of this total decay rate, you can calculate the partial decay rate for the single beta decay, which is here. And the expected single beta decay rate is 1.6 times 10 to the 19 years. Experiment is greater than 2.6, so there's a bit of tension, but they do not discard each other. There's a little bit of tension between. The prediction is from the QRPA, it was 24. The Q value measurement is essential because this matrix, or the half-life, because of the phase space, scales with the 13th power of the Q value, because it's a forbidden decay. And it's a unique forbidden decay, as I alluded to already here, so it's this one to that one. The ground state is six-fold non-unique, you can forget it, 10 to the 30 years. And the one to the 4 plus is four-fold non-unique and has no phase space available, it's also 10 to the 28. So this the only possible one is there. So once you have the matrix element, you can compare the matrix element with these neutrinoless double beta decay, because there you also have the four-fold forbidden matrix element in there, but at higher momentum transfer, of course. But as I said, you can compare it with the same nucleus and with the same theory. To make a long list short, this is the value that came out. So, okay, and the values had changed according to the mass tables in 2012 by a significant amount, about 10 keV. So the Q value came out to be 163. Klaus Blaum showed you these Ramsey time of flight measurement. I don't want to go into this. Okay, once you have the Q value, the next thing you have to look for the half-life. So, okay, so the half-life is predicted by the QRPA to be 24 divided by GA squared, 10 to the 19. By the shell model, 11 divided by GA squared, 10 to the 19. So the shell model and the QRPA differ by more than a factor of 2. This is worrisome. For me, this is worrisome because they calculate the same thing. So it's important to measure that, but there is a side effect, a very important side effect. The single beta decay depends on Ga squared. The two neutrino and the neutrinoless, they depend on Ga to the fourth. The two neutrino is known. The single beta decay will soon be known. Theory has to describe the two neutrino one and the single beta decay, and then you get a ratio of these two things because one depends on Ga squared, the other one on Ga to the fourth, so you have a handle on Ga because of the differences there. So in terms of measuring, it's very easy. Well, not easy. But you look for the zirconium decay into the 5+, it trickles down to the ground state, and after 23 hours, this one decays to the molybdenum, or it's lost here, and it all ends up at 2+ state, and the final de-excitation is 778 keV. So you look for the 778 keV signature, which is easy to do. Well, relatively easy to do. And from there, you can deduce the half-life and get some handle. And then you tell this to your theory friends. Muon capture and zero neutrino double beta decay. Switch to a completely different field. So the motivation here is muon capture features a momentum transfer which is similar to the neutrinoless double beta decay, or the 50-100 MeV over C. Okay? Muon capture processes, or capture processes, to 1+ state make or can be compared with charge exchange reactions of the NP type. Let's say dihelium-2. One is at high momentum transfer, the other one is at low momentum transfer, if you can do it. Okay? So if you do that, and if you manage to be able to do that, you get an access to the Ga. I show you this, how that works. However, little caveat, the only thing that matters is the zero neutron decay channel, okay? So that's only 5% of the muon capture. 95% goes into 1 and 2 and P and these type of things. So you want to go into the really intermediate state. Okay, if you do muon capture, you always end up in an odd-odd nucleus. This is really bad, because odd-odd nuclei are not known at all. The level scheme is atrocious. So this is zillions of levels, so you have no chance to pick out a particular transition. However, there are 3 exceptions, fortuitously. These 3 exceptions we want to investigate at RCMP at the Muon facility, and there's been a letter of intent, exclusive muon capture of magnesium, sulfur, and iron-56 populating low-lying 1+ states to probe the weak axial current at high momentum transfer. So this is my former student, Milad Al-Ansari. She's working on that and is the PI on that. I have 2 more minutes. I like muons. Muons are an amazing particle. Why? Because there has not been any other elementary particle that has given us more information about so many fields in physics. Particle physics, nuclear physics, solid state physics, you name it, cryophysics, you name it. So muons are being created, as you know, by pions. Pions decay, and then you have the muons. You typically go to 500 MeV with the proton beam. Here you want to use surface muons. Surface muons are being created by the pion that is at the very end of the target, stops and decays into the muon, and the muon has an energy of 4.1 MeV, which is 30 MeV over C. To give you an indication why muons are so wonderful, so the muon lifetime is very, very well known, okay? And the mass here is 8 significant digits measured from this thing, from this exotic hydrogen. Why was that important? Because these 2 things give us the Fermi coupling constant. There is no other way to get the Fermi coupling constant. And you see there are 6 significant digits on the coupling constant here. And it's only due to the muon. So muon capture is nice, Because the muon comes in, is being captured by an atom, and trickles down woof, into the ground state of the atom. It's like this, boom, 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 and goes down here. So the typical, and then it resides in the K shell, and a couple of 100 nanoseconds it's been captured by the nucleus. So you get a flash of X-rays as a prompt, and a couple of 100 nanoseconds later, typically, you get the gamma ray. So the typical thing here, if you don't know what the half factor is, don't worry about this. So the total lifetime here of the muon is then somewhere between 10 and 1,000 nanoseconds, typically. And is reused, of course, from the 2.2 microsecond of the free neuron. So the the neutrino takes most of the energy away, so the energy that is dumped into the nucleus is of the order of 10 to 20 MeV. So now comes the story. D-helium-2 has been measured in iron 56. I'm going to these 3 nuclei, which are really special because of the low energy part. So we have a low energy BGT of this one at 110 keV, which resides here. That's the 110 keV. We of course have more BGTs here from the D-helium-2, but these are not identified in the level scheme. We don't know how they decay. But this 110 keV state decays via gamma cascade, which is very well known. On top of this, we have the BGT here. On top of that, we have the BGT from the beta decay from the other side, populating this thing. So this state is extremely well known. And it should be extremely well calculated by a theory. It's a PF shell nucleus, so it should not be a problem. Okay, so the next one is sulfur-32. Sulfur-32 we have, again, D-helium-2. There's a state, a very strong state, 1147 or 1149, and that state is known in the level scheme. Remember, it's an odd nucleus. It's known in the level scheme, and the level density is very low. So this one makes a gamma cascade down into this. If the muon comes in from the side, populating this level, you can see it from the gamma decay. How to do this? I come to that. And the last one, and this is the only one left, is the magnesium-24. D-helium-2, again, we have now 2 states here. This one here, you cannot place in a level scheme, but these 2 states are very well known. This is the one here, has a complicated gamma de-excitation, and this one has also a complicated gamma de-excitation. So you look at the gamma de-excitation, and you want to measure what is the side feeding from the muon capture. Okay, so do you do that in a typical way? People who've been at PSI then know that there's a muon beam, this low energy from the surface muon. So you have some aperture defining detectors in here. You make sure that the muon goes through these 2 detectors, being stopped in the target, not hitting the 3rd detector, and then you have a muon capture. All the muons capture, all of them, you know, all capture into the atom and create a flash of X-rays. So in order to get the X-rays properly, you have to come up with a Clover array on this one. And this is done at CNNP, where there's a Clover array there, because the muon populates high energy states, and all these gamma rays come down, 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 down. But you want to have the side feeding of one particular state, so you have to do some detailed balancing, and that's only possible if you do gamma-gamma coincidences. And that's done here on the muon part with this Clover array, which is being constructed at CNNP. So we're looking forward very much to do these experiments in the next couple of years. They're not easy to do, these experiments, but I hope we can get forward on this for the next 2-3 years to go on this. So the issue of GA quenching. So hold your horses a bit. Things are a bit more complicated. There is, in the muon capture process, there is also a pseudoscalar effective coupling constant. So what is the pseudoscalar part? The pseudoscalar part is, inside the nucleus, the muon can decay back into a pion, virtual pion, lots of energy available, and the pion generates a final state, imprinting it with the parity of the pion. So that makes a pseudoscalar part. However, we have 3 different nuclei where we can test these things, because the pseudoscalar part should be different, or the pseudoscalar response should be different for the different proton to neutron ratios. So this has 12 protons, 16 protons, and 26 protons. So that should be able to disentangle the pseudoscalar part from the axial vector part. And then you compare. What is the axial vector coupling constant in muon capture for this state, and what was it in d-helium-2 in charge exchange reactions? Conclusion, I'm done. Charge exchange, still useful. Spin dipole for the first time, a big surprise. The theoretical models we have looked at fail for this. I don't know why. Precision mass measurements, zirconia I showed you, is a golden case for testing neutrinoless double beta decay nuclear matrix elements by simply measuring the single four-fold forbidden decay, and it gives you also a handle on the GA. And of course, the muon capture may be the only viable option to study a weak response at high momentum transfer and to fix the GA problem by comparing it with something that is at low momentum transfer. And we do have some data, very good data at low momentum transfer. Thank you very much. I overdid my time, I guess.